Alrighty guys, what I'm going to do here is I'm going to unpack a little bit of that impulse or the change in momentum. So the first thing we're going to do is we're going to bring that formula back. That impulse or change in momentum is denoted by one of two different things. Could be your mass, your momentum final minus your momentum initial. If the masses of those objects stay the same, it'd be just mass times your change in velocity. Now, the other part of the formula on your reference sheet is that it can also be denoted as force times your change of time. So with this, we can note a couple of different things. If your mass does not change, so no change in mass, but there's a change in velocity, then you're probably going to want to use this formula. If there is a change in mass, so if there's a change in mass, but not necessarily a change in velocity, but no change in velocity, or it could be both change in mass and change in velocity, then you're probably going to use this formula. However, the last one we're going to talk about is what does this force and time interval looks like. So anytime you see newtons, or you see acceleration, let's try that again. You see acceleration, because if you know acceleration, the mass of the object, then you can then use to calculate F net by saying mass times acceleration. And then your time interval, like I said before, is usually a small number. Because if it's a large number, then it usually turns to more of an energy question rather than a momentum question. Although it can still technically be considered a momentum question if certain conditions are met. Now, when you find in this class that when you have impulse or graph that has mass and, force and time, from here you can calculate a couple of interesting things. So the first thing it's going to be is, let's draw a graph here. Well, I have clearly a positive force for some time interval, and then I have a negative force for some time interval. Well, what does this tell me? This tells me that since this had experienced some positive force for some time, let's try a different color here, that this would be considered a positive force for some time, and that would be your impulse right here. And that would be denoted as positive. Since the force on it is positive, times your delta time, change in time, which is always going to be positive, that tells you your impulse here is going to be positive. Meaning A, your object was either speeding up to the right, or it could be slowing down to the left. Because remember, momentum is a vector unit, so if your object's already going left, it's got negative velocity. Positive impulse means you're speeding it up in the right direction or slowing it down in the left. Now, down here, we have our negative impulse. So we're going to say the delta P here is negative. So it's force negative time for some time interval. And so that means the object is speeding up to the left usually, or slowing down going to the right. And so to find the final momentum of an object, you're usually given your initial momentum. So for example here, let's say our initial momentum was given. We would use our formula like so. We would say that the change in impulse of an object, or change in momentum of an object or impulse, is final minus initial. Usually in these types of questions, you're given your information you need right off the bat. You just gotta learn how to unpack it. Well, this piece right here would be the part that comes from your graph. Okay? And then in the pretext of the question, usually you can find initial or final momentum. 9 times out of 10, it's usually looking for final momentum. So final momentum is going to equal delta P plus your initial momentum. From there, all you need to do is find the area under the curve, mass and velocity, and then find your answer from there. However, I have seen a couple of tricky things pop up where they want to find your final velocity, not necessarily your final momentum. So it would be delta P plus your initial momentum all over mass. And that would then, I'm going to divide by mass over here so these cancel out. And so depending on your situation, final velocity is usually calculated this way. All right. One thing I wanted to note here is that this is delta P, and that is not momentum. It is your change in momentum. So it doesn't tell you much about the beginning or end of the object. It just only tells you how much it was changed. Okay. Next thing we're going to do is look at some special case examples of how things like to get screwy. So the first thing I'm going to do is let's go through a little bit of a thought experiment. If I have an object that's colliding in a wall at an angle, we'll call this a perfectly elastic collision, meaning no kinetic energy is lost. It's going to hit the wall, and then what is it going to do from there? Well, what it's going to do is it's going to continue bouncing off at an angle. Well, what does this look like mathematically? Well, since this is in two directions, we're going to have to write out our equations in two directions. We have a momentum in the y direction that stays the same the entire time. So it's staying positive in that y direction. So momentum before equals momentum afterwards in the y direction. So let's do y direction. And that we notice here is that since it doesn't change, whatever your momentum before is momentum afterwards, meaning there was no change in momentum, and that means there was no force applied in the y direction for some time. Because since this comes out to 0, delta P equals 0, which means there is no force acting in the y direction. Now this is going to help us real quickly in a second when we look at what happens in the x direction. So let's do that. Let's use blue to say that the momentum in the x direction is here. When it makes contact with the wall, it has 0 x velocity. So what we're going to do is then say, okay, up here it's 0. So we're going to say momentum in the x direction right here. This moment is 0. And then up here, it's then going to be going back again to the left. You would notice if I add these two vectors up, it would equal your resultant vector. So let's look about this in the x direction. Now, that means momentum before equals momentum afterwards in the x direction. And so what this tells me is that it is changing, and so that there is an impulse in the x direction. Now, since impulse is also calculated by final minus initial, we can say momentum final minus momentum initial equals force times your change in time. Now, here's one thing I wanted to denote, and people love to get mixed up, is that we can agree if something hits a wall and bounces off, some force is going to be pushing back on it. That's usually going to be force normal. Where does this mathematically come to where people are going to cancel out and come to 0? So I'm going to do this wrong first, erase it, come back and do it correctly. So let's do like a light blue color for when it's doing this wrong. So what students might say is, okay, mass is going to stay the same. So it's going to be mass times your change in velocity. We're going to call that velocity initial or velocity final, and we're going to say that's minus velocity initial. And let's say the object was moving at 5 meters a second, so I get 5 minus 5. So mass times 0 equals this. And so my object experienced a force of 0 from the wall. Well, that automatically breaks a lot of things we've already been talking about in class, and that's not what we want to do. So instead, we have to pay attention to our signage here. So we notice is that this is correct. What we're going to do is, how do we fix it from here? Well, our final velocity is going to the left, so that it is going to be the same. But our initial velocity is going to the, our final velocity is going to the left, so that's going to be negative. Our initial velocity is going to the right, so that's also going to be negative. And so what we notice here is that if this is an elastic collision, these numbers are going to be the same, and what we find is mass 2 times of your initial velocity in the negative direction is going to equal force times your time. Now, what this tells me is in any elastic collision, any elastic where it bounces off, your impulse that's felt on the wall is going to be 2 times your momentum. Now, it might be a nice thing to shove in your back pocket for later, but here's one thing that people tend to get tripped up on is not noting your signs here in the directions you're going. So this tells me, since mass is a positive number, my initial velocity is a positive number, that means my force exerted on from the wall is also going to be, has to be a negative number, since I have a negative over here. And why is that? Well, when this ball makes contact with the wall, what direction does the wall push back on it? And that would be to the left, which would be a negative force. If we were to flip this over, the equation would be the exact same, but it would be positive force, could be pushing to the right. Okay? And we're going to wrap this up as part 2 of our